it doesn't really matter if you start a process as a thread, as a coroutine with a global scope, or as an async class. In all those cases, you started a process that is asynchronous in relationship to your whole program. And that generates problems. You see, there are mechanisms to synchronize those processes, but it is easy when you have only two processes. But the more and more of them you have, the harder it is to manage them. And then we can see real problems with concurrency. In a way, it is similar to this classical go-to statement that you hopefully do not need to remember about, that was extremely powerful, but at the same time highly uncontrolled, and got replaced in modern programming with control structures. We'll get back to that later in this presentation. The same process is now happening with concurrency. And the solution to the concurrency problem is structured concurrency. My name is Marcin Moskała. I'm a consultant, trainer, and contractor, JetBrains partner for teaching Kotlin, GDE, and Android, author of 6 books about Kotlin, including Kotlin Coroutines Deep Dive and a big learning experience, Coroutines Mastery. I don't think I need to tell you about it. If you haven't heard about it, I guess you will hear about it soon. So the essence of structured concurrency is, of course, building relationships between our processes. In Kotlin, in Kotlin X coroutines, this is how those relationships typically look like. We start coroutines on a scope, we launch them, and then if we need to start asynchronous sub-processes, we start them on a coroutine scope. But of course, structured concurrency nowadays is not only in Kotlin X coroutines. Kotlin X coroutines was one of the pioneers in this area, one of the early adopters of structured concurrency. But this paradigm is now present in many languages, including Python, Scala, Java, or Swift. The tree, the structure looks very similar in all those technologies. This is how it would look like in Java. We would start threads on executor, and we would also create a scope to start sub-processes. But let's concentrate on Kotlin X coroutines in this presentation. I just want you to know that nearly everything I'm telling you here is applicable to those other technologies, because it's a modern consensus for how structured concurrency should work nowadays. So let's start with 2 main concepts. How do we start coroutines? In Kotlin X coroutines, we launch coroutines on a scope, which associates those coroutines to this scope, makes these coroutines children of this scope. On Android, we use our scopes like viewModel scope, lifecycle scope, and remember coroutine scope, which are associated to a specific view or a component. You can also launch coroutines in other ways. In case of flows, you use launch-in or state-in or sharing, but all of them launch a coroutine on a scope, typically using launch under the hood. Now, starting sub-process. If you are already running on a coroutine, you shouldn't start new coroutines on a scope. You should first create a new scope, a scope with a coroutine scope. Such a scope is a children of a caller coroutine. So whoever called this function will be a parent of this coroutine scope, and from which you can start asynchronous coroutines. What you shouldn't do is that you shouldn't start coroutines on a scope, because that would make those coroutines children of this scope, so it would break structured concurrency. They wouldn't have any relationship to the caller of this scope. So this is an incorrect pattern. How does it work in Kotlin? Everything is based on 2 mechanisms. First, the implicitly passed scope. So the asynchronous coroutines are started on a scope. They also provide a scope for inside their lambdas, so that coroutines started inside those coroutines are children of those coroutines. But what about coroutine scope? Coroutine scope provides a scope for asynchronous coroutines, but it also builds relationship to the caller. How can it do that? Every suspending functions implicitly passes a continuation. Continuation can
can access a coroutine context. Coroutine context includes the job. This way, coroutine scope can build this relationship. There are a few ways how this structured concurrency can be broken. One way is to launch something on a scope. This is sometimes acceptable if you know the consequence of this process. This is a way to start the background processes, but it breaks structured concurrency because it associates this coroutine to the scope, not to the caller of this function. Other approaches are considered absolutely unacceptable. Launching coroutines with a job, or using with context with a job, or supervisor job, all of those are considered an anti-patterns in modern programming. You should also know that in flows, the relationships are also built in exactly the same way. Flows respect structured concurrency. So if you define some complex flow, inherently by default operates on a single coroutine, but there are some processing functions that start new coroutines, like buffer, that start a new coroutine for everything above, or flat map merge, that start a new coroutine also for everything above, but also for sub-processes. So here we would have a hierarchy of coroutine that is associated to the caller of this flow. So the caller would execute map function, but then there is an asynchronous coroutine started by buffer and asynchronous coroutine started by flat map merge. They also synchronize with each other by using channel inside. All right, now you know how structured concurrency is built, how to maintain it, but why do we have it? What problems it solves? And when I asked Android developers about it, most developers only think about cancellation, which is one of the reasons why we use structured concurrency, but only 1 out of 5 key problems that structured concurrency solves. So let's talk about them one after another. Cancellation is the simplest one, most obvious one for Android developers, since we treated cancellation very seriously since early days of Android development. And structured concurrency gives us effortless, simple cancellation. If you cancel a scope, you cancel its children, you cancel its children, and everything gets canceled. Let's see it in practice. If you launch a coroutine on a scope, if you cancel this scope, this coroutine gets canceled, coroutine scope gets canceled, async functions get canceled, and requests also get canceled. Is it important? How much we can save on that? And here I prepared a very clear example of how much we can save from this basic cancellation mechanism. Imagine that you, this also works in backend. If you make a request using a suspend function, define a request using suspend function, if you lose HTTP connection, this function gets cancelled, its children gets cancelled, async gets cancelled, everything gets cancelled. Okay, how much can we save thanks to this mechanism? So imagine that you implement a service like a sky scanner that I used to find flight to get here on this droidcon. Now on a sky scanner, you are searching for the best flights, but to get the best flights, you need to make requests to all the different providers to know what flights we have available. Now, this is very expensive because that very likely starts many requests to many services. Actually, every such search costs cents or close to $1 in extreme cases. Now, imagine that a user started a search, but immediately left it because maybe he decided he needs a different date or he needs a different airport, so immediately left the screen. So without structured concurrency, in most typical front-end application, even though user would change the screen, the previous request would still remain active and all the requests going on in the background would still keep being made. Now, with structured concurrency, of course, a process of fetching connections is associated to the scope of a view. So once view is disappears, we should have this process cancelled, and in result, this connection should be cancelled. And if structured concurrency is also used on backend, the cancellation of a request or of a WebSocket should automatically result in cancellation of all its children, so fetching all connections and immediate cleanup of all the requests. So that can save us a lot of money, and it does save us a lot of money. We knew that since the beginning of Android. We treat cancellation very seriously, and structured concurrency haven't gave it to us. It just made it much more simpler for us. But that's not the end of the structured concurrency advantages. Here is something that we haven't got before structured concurrency. That was actually one of the big selling point of structured concurrency, exception handling. I guess it was one of the biggest selling point in Java to introduce it over there. So let's get back to this simple example where in a process we start asynchronous sub-processes like fetching flights and hotels at the same time, so that user can wait less time to receive this response. Now, what should happen if one of those requests throws an exception? If, for instance, search hotels fails. Now, what do we expect to happen? We generally would expect this search to throw this exception, but we would also expect, and we would expect it as soon as possible because why waiting? And we would also expect search flights, the other request, to get cancelled. And this is what happens thanks to structured concurrency. Exception is propagated to coroutine, to async, propagated to the parent, coroutine scope, cancels children, so async, so it cancels search flights, and exception is thrown. Now, it might look obvious, but it isn't. And making this work this way was actually quite hard. And it required this coroutine scope. That's the main reason why this coroutine scope is in every technology implementing structured concurrency. It has different names. In Java, it is also called a scope, but in Python, it's called nursery. But it must be there, and it is there in all libraries that support structured concurrency. Why? Consider alternative approaches. Let's start with the most obvious ones, one where coroutines are started on a scope instead of on the color of a coroutine. We already know it's incorrect because it breaks our tree structure, but how would it behave in terms of exception handling? So if we had an exception in search hotels, this exception would be propagated to the scope. What would this scope do? Well, we don't really know. It might fail and cancel everything inside of it, but more likely this scope is using supervisor job inside. And at least in theory, because in practice in Android it would break our application at the moment, but in theory, if we overwritten a coroutine exception handler, this scope would ignore this exception. So if this scope would ignore this exception, what would happen to our search function? Would it throw this exception? Well, finally it would, but it would first await for the completion of search flight. So the process of searching flight wouldn't get cancelled. We would need its completion because its await is first, and only then we would throw our exception. So I hope you can see it's clearly not the right behavior. Okay, so let's now consider another approach that used to be pretty popular at early days of Kotlin X coroutines, starting those sub-processes directly on the caller scope. So no super coroutine scope inside our function. We just pass coroutine scope either implicitly as a receiver or explicitly as an argument. Doesn't really matter. We pass our caller scope. What's wrong with that? Let's analyze the same situation. Search hotels throws an exception, so this exception propagates to async. and async propagates it to its parent, so directly to the parent scope. Now, how would this scope react to that? Again, we don't really know. If this were a supervisor scope, it would ignore it unless we are on Android and coroutine exception handler breaks our application. But let's say, most likely it wouldn't ignore it. Most likely this scope, this coroutine would break, would cancel. Okay, it would cancel other children, but it will also cancel everything else. So we wouldn't be able to safely catch this exception and handle it. So one of the most basic presupposition about functions, when you call a function, you expect that if this function fails, it throws an exception. You don't expect it to break your coroutine. Yeah? So one of the most basic presupposition of functions would be broken. And that's why this approach is incorrect. And also search flights away would call coroutine exception handler, not the exception from search hotels, but that makes very little difference. This is clearly an incorrect approach. Okay, so what other advantages do we have from structured concurrency? Because we covered only 2 of them so far. Another one is configuration, something that is used also quite widely in Android. So thanks to structured concurrency, the configuration of our coroutines can be only specified in the scope, and it is automatically propagated to all its children. And as you know, you can change this configuration. We especially often change our dispatchers, and if you specify a dispatcher from a coroutine, it is set not only for this coroutine, but also for its children, which makes configuration management, dispatchers management much easier and much more intuitive, which is a great advantage on Android. Another one is observability. Here I used a screenshot from a plugin that is drawing a nice hierarchy of coroutines. In a typical debugging session, we have this list that we can extend, but it doesn't change the key idea. The key idea is that thanks to the fact that our coroutines are structured, we can more easily analyze them and analyze what's going on in our application thanks to that. Like a simple example, imagine a backend, will be a bit extreme. Imagine a backend application that handles 100 requests, every single one in a different coroutine, and every single one of those requests, let's say, have on average 10 asynchronous sub-processes. Now, without structured concurrency, you would have 1,000 coroutines, and you wouldn't know what is the relationship between them, which one of them are handlers, which of them are some sub-processes. There would be a complete mess. Okay, internally they would wait for each other, but analyzing that would be extremely hard. Now, with structured concurrency, you have a nice coroutine per request, and pretty often you can associate those coroutines to requests thanks to the specific context we associate. And then for each of them, you could analyze what sub-processes are currently active, which gives us much nicer observability. And finally, the last one, I left it to the end. It is the hardest one to explain, but it was the main reason, the main argument in the original papers supporting and promoting structured concurrency. So some will argue it's the most important argument behind introducing this technology, this approach. The clarity of our application. So before we understand it, I want to get back to this go-to metaphor. So before we had in the ancient times of programming, one of the most basic basic block to control our application was a go-to statement. Go-to statement was a statement that allows execution to jump at a specific line of code. Now, go-to was extremely powerful. It could be used to replace all the control structures that we have, for loops, if statements, functions, whatever you wanted. But it was too powerful. First of all, it made our code extremely hard to analyze. But it also made many other blocks impossible. So for instance, if we had go-to statement in our program, it would make no sense to have a try finally block. Why? Because this try finally couldn't guarantee that finally is called if you can jump out of it, out of the try block. You cannot guarantee that a resource is opened if you can jump inside this block. Many things make no sense if we allow go to statement, because it is uncontrolled. It has no clear entry and exit point. And the solution to the problem with go to statement was functions and control structures. And the key characteristics of those was that they all have a clear entry and exit point. It doesn't matter what happens inside. You can loop inside, jump inside, whatever you want, you can do it. But for every function and every control structure, you have a clear entry and exit point. And thanks to that, you can analyze this block in separation from anything else in your code. You know nothing will jump inside of it. You know nothing, you cannot jump outside of it. You have clear entry and exit block. And if you go in here, you must go out of here. That's like with kids on a kindergarten. It's much better to have the, attractions where you know that if kid goes in from one hole, it goes out of another one. If there are multiple, have fun. See? Now, the same problem we have with concurrency. As I told you, if you start a process that is asynchronous in relationship to our program, it is very hard to control it because you finished your function, your block, but you don't know if what was started by this process isn't still going on and isn't still making some changes that we might not be aware of. And the solution to this problem is structured concurrency. This is exactly why functions like coroutine scope functions, coroutine scope, supervisor scope with context with timeout, this is exactly why they must await their children completion. Why they cannot allow these children to outlive the scope itself. Because only then we can think about suspending functions or about coroutine scope as a block of code in separation of what's going on outside of it. It's like with this control structure, it gives us clear entry and exit point, and you don't need to think outside of it. I know it might look very unclear at this moment, but I will show you two examples. Exhibit 1, awaiting processes. Let's say that I create a unit test that starts some asynchronous process inside of it. And inside of this asynchronous process, I have some assertions. So this assertion should clearly fail, but of course this test wouldn't fail for two reasons. One reason is that an exception inside this thread wouldn't be propagated to the function itself. And the second reason is that this test wouldn't await this thread completion. So this test would complete immediately, and this assert equals would be called after this test is completed. So both of those problems are solved by structured concurrency. When you use run test, it must await its children completion. It can sometimes be annoying when we have coroutines that work forever and we need to close them or cancel them. But it guarantees to us that by default, if you start some sub-processes, this sub-process won't be ignored, won't be forgotten. That run test will await the completion of this launch. Launch will wait 1 second, make this assertion and fail, which is an expected behavior. Okay, this is given to us by structured concurrency. The same with the main function or many other things. If in main function you start a bunch of coroutines, suspend main, to start a bunch of coroutines, you must use coroutine scope, and then coroutine scope awaits the completion of those coroutines. That is given to us by structured concurrency. Exhibit B, closing resources. I mentioned that already. Try finally. I will, for the simplification, use this use line functions on a file. I hope you know it. It's a function that opens a connection to a file, gives you a sequence that allows you to read lines from this file, and then closes a connection to this file. Yeah. Now, this is a very popular block. We have many such blocks that are closing resources in finally. And that, of course, is based on the assumption that the lines and the processes started inside of it cannot outlive their execution. So if we finish the lambda, everything that it was doing is finished as well. And of course, this pre-assumption is respected if you extract a function out of it, or if you use any control structure inside of it. All of them will perfectly respect it, so this is fine. But this pre-assumption wouldn't be respected if you start an unstructured concurrent process. So, for instance, if you used a thread, now you won't see any lines because thread starts a process, but consume lines immediately ends, closes resource, you cannot read this file. Okay. Can you see the problem? So structured concurrency isn't allowing that. If this were a suspending function, to launch a coroutine, to start a coroutine, you would need to wrap it with a coroutine scope. Coroutine scope would await the completion of this coroutine, which of course would make this launch a nonsense if it does nothing, because it starts an asynchronous process, but the coroutine scope synchronizes it. In this case, it makes nothing. We can replace it with a regular function. But in general, as you can see, structured concurrency gives us the same guarantees that we generally expect from functions, that their sub-processes cannot outlive the process itself, cannot outlive the function itself. So if function is completed, what it was doing, what its all sub-processes are completed as well. Okay? And this is the key idea of structured concurrency. So to remind you, there are 4 problems that structured concurrency solves: cancellation, exception handling, configuration, observability, and clarity. I hope that after this presentation you will have a deeper understanding of this concept. I also go much deeper into structured concurrency and other coroutine-related concepts on my course, Coroutines Mastery, a 5 weeks course. It starts next week, so another occasion will be next November, next year. And we already have 150 people. We'll have a great 5 weeks. I think we'll have a lot of fun. So yeah, it is something I'm very excited about. This was everything. I would like to welcome you for questions, and for now, thank you for your attention. I can see there are microphones here and there. If you have any questions, ask me anything. It doesn't need to be related to structured concurrency. It can be related to absolutely anything else, including my work, my courses, my I don't know. Yep, go ahead. Oh, I will repeat this question. Don't worry. Mm-hmm. No, yes, in a sense. Yeah, so the question is about dispatcher, or in general about context propagation in flows. So when we start coroutines inside flows, what is their context? So the rules are very similar as as with suspending functions. So let me just find it. Okay, here it is. If you don't change the context, because there is of course flow on function to change the context is inherited from the color coroutine, just like with a coroutine scope. So functions like buffer, or conflate, they both start an asynchronous coroutine for what is above. And they send to the coroutine from below, and they communicate via channel inside. So this coroutine sends to this channel, those functions receive from this channel, and of course, depending on the size of your buffer or the conflation option, and the behavior of this, the configuration of this channel is different. Yeah. But yeah, by default, this coroutine is started on the scope of this coroutine, just like with coroutine scope. And the same with flat map merge, it also is started on the scope of this coroutine. So by default, the context goes from down to the up, unless you change it with flow on changes it for everything above it. Simple heuristic. Anything else? Oh, sorry, there is a hand over there. You have a microphone quite close to you, so it might be nicer to others in here. Can you turn it on? That doesn't work. Okay. Mm-hmm. Can you get slides? Yes, I will publish them on my Twitter. It's at Marcin Moskała, just like my name and surname. All right. If you have any other questions, please find me around. I will also find a way to give away books. Maybe I will make a contest again with my coroutine games. Maybe this time we'll use my flow processing game, a new one. Yeah, it will probably happen soon. For now, thank you again, and have a happy conference. Yeah.